What's up, guys? Today we're going to talk about having more than one buffer, or more than one attribute. So this will be sort of an attributes revisited video. So let's see where we ended up last time. There we are. Cool. So we have a rolling square that changes color. How exciting! However, what if we want to have one color per vertex, right? So we want to have not the same color for every single pixel. We want to do maybe one corner is red, then one is green, and one is blue. So how would we do that? There's certainly a lot of ways to do it, but I think the easiest one is to define another attributes for each of the vertices, right? So we're going to define a one color for every vertex. And this is, a common attribute to have if you're working in Maya or Blender, for example. There's something called vertex painting, where you can paint over the mesh, and what you're doing is actually painting each of the vertices a certain color that can be red then in Unreal or Unity to do something. So let's do that. First of all, I'm actually gonna make it stop moving for a little while, just so we can see a little bit more clearly what's actually going on. So I'm actually gonna go into the Vertex Shader and just comment out this code for now. So I'm gonna comment it. The comments work the same as in C++ and C# and so on. So there we go. And in the Fragment Shader, I am just gonna return white for now. So I will comment this out, and I'll do the colors equal to. I'll just do red actually, just to distinguish it from the error shader. Since if a shader has an error in it, it will return white. Okay, there we go. Nice red, flat, square, rectangle. It's a square. Yeah, okay. So we want to define another attribute. So let's go into paint actually. Oh, God, it's so bright. I wish I got like default black or something. So right now, I'm gonna have so much shit on my desk. It's like tea and there's water and oh dear. Okay. So right now, our vertices, we only have one attribute. We have a position, which is the position of our vertex. So, and that's mapped to some data. So you know it's 0.5, minus 0.5, 0.5. I don't exactly remember the order, but it's something like this, and so on. And that's our vertex buffer. This data. And we're grouping, we're taking each pair of two and mapping that to each vertex a position. And then we're taking the next two, and that becomes the second vertex, and then, so on. So the easiest way to do this would probably be to, or I shouldn't say easy, I would say the simplest way to do this would probably be to make another buffer for the color. So we'll make another buffer, another VBO, that instead of containing positions, we will contain the color. So we'll do 1, 0, 0 for red, and then we'll do the next vertex. So we'll do that like let's only do RGB. We could do RGBA if we wanted to, but let's just do RGB for why not. The next one will be green. So we'll do not 0.1. 1.0, 0, 0, and then so on, whatever colors we want to define for our vertices, and we will make that a color. Whoops. So we'll define another attribute that's the color of each of the vertices, and then we'll group that in groups of 3 like this, and that will become each vertex. So the way this works is that it just takes them one at a time, all right? Every time the vertex shader is called, the first vertex will take, the first group of position and the first groups of colors and set those to each of the attributes, right? So the first vertex will have a position 0.5, negative 0.5, and a color 1, 0, 0. And then the next vertex will have, the next set of positions, 0.5, 0.5 will be a position, and then 0, 1, 0 will be a color. So we'll just take them, in order and group those together into one vertex. So we can sort of, we can group this together like this. So this is one vertex, this is the second vertex, this is the third vertex, and so on. And again, these bindings to which VBO goes with attribute and how is kept track of by the VBO. No, it's not the VBO, VAO, the vertex array object. Cool. So let's do this. So let's see here okay, so here's the position data. So I will just go ahead and make another one. So we'll do color buffer contains the color. I don't know, that's the not the most enlightening comment ever, but whatever. So I'll just call that color buffer. Will be the handle, and then I'll just gen another buffer. This will be essentially exactly the same code as above, and then I'll bind it. GL array buffer color buffer. All right, so let's define some color data then. So we'll do color data is equal to, whoops. So we're gonna group it the same way, because nothing's gonna change about which vertex index. The element buffer will still be there. It will still work the same way. So we just have to pair these together. So if this defines the lower left vertex, that's the first two values, then we gotta make sure that the first three values in our color data maps to the bottom left vertex, and I'm gonna make that red. Okay. So the bottom left vertex, as I'm seeing here, will become red. Okay. And then the next one is the bottom right. So I'll make the bottom right green. And then it's top right, and I'll make that blue. And then it's the top left, and I'll make that white. Like so. Don't forget the semicolon. So that's going to be our color data. And important to know the groupings. Like these two are a pair in one vertex. These two will become a pair in one vertex. These two will become a pair, and so on. That's how we want it to end up, at least. That's how we're deciding how we want to group the data. So I'll do GL buffer data, GL array buffer. Just again, this means uploading data to the bound VBO. And currently we have the color buffer as the bound VBO. So that's where the data will end up. So the size is size of color data. Pointer is just color data, and GL static draw will work fine. Okay, so now we made a new buffer. We made a new buffer. We put some color data in there. Now we want to bind the attributes. Okay, and if you guys remember, the attributes, all of that happens in the VAO. Let's just make a comment here. This became very messy. Let's do load the shader program from our nice shader files. There we go. I was confused about how much code there were. Okay. So the VAO keeps track of the attribute bindings. So let's see here. So we're creating the VAO. We're binding it. We bind the EABO here, the element buffer here. So make sure that our VAO keeps track of that. That doesn't matter right now. Okay, and here we go. Attributes. Enable attribute 0, and we're binding attribute 0 to be a vec2. So two floats. Not normalizing it 0, 0. Okay, so let's just do the same thing for attribute 1 in this case then. So we'll just take the next value, attribute array, and then we'll do 1. And then we'll do, okay, vertex attribute pointer. The index is 1, so the attribute 1. Size, so that's how many components, and this is a vec3 RGB, so we'll do 3. And type is going to be float. Normalized, again, we don't want it normalized. Normalizing means that it will make sure all the vectors are always size 1. So for normals, for example, if we have an attribute that is the normal vector of the vertex, we always want to make sure our normals are of size 1. So then we might check normalized true. Although I don't think this is very used. Usually just normalize them yourself when you're actually uploading the data to the VBO. So let's type false. And then again, stride and pointer we'll come back to soon, so we'll use type 0 here for now. And let's compile it, and it works, and let's see what happens. Okay. That's not good. It went away. And we didn't even implement the color in the shader yet. So how can binding a new attribute break our quad? That makes no sense. So, okay, there was something we did. I'll tell you right now, it has nothing to do with this. There is something we wrote that fucked everything up. And I want you to guess what it could be. Sort of think about it for a second. What have we done? And the key knowledge here to understand why this is going wrong is to realize when we call this GL vertex attribute pointer, what we're doing is that we're binding a VBO to an attribute. All right, so here's where that link happens between vertex buffer to attribute and how it's bound. And we don't even input any VBO here. We don't input a handle. So we don't say like, oh, this VBO, link it to this attribute. So where does it get the VBO from? Now, how does it know? It looks at the currently bound VBO. So that's the key information to understanding why this goes wrong. It's looking at the currently bound VBO, and that's where it makes the link. And if we look at the order we did things here, we first did a vertex buffer object for position. We bind it. So here it's bound, and then we upload data to it. And then we create the color buffer. And here we bind it. So what's happening is that whenever we get to the VAO code, the currently bound buffer is going to be the color buffer. So instead, what we're doing, instead of making this link from a position to our position buffer, we're instead making the link from a position to our color buffer. So what's going to happen is that it's going to go, okay, these two are one vertex position, these two are one vertex position, and these two are one vertex position. And, if we look at them, it's kind of nonsense data when you think about it from like a triangle perspective. It's like, okay, 1 0 0 0 1 0. That's just going to be a line. So like, that's not going to be visible. And then it's going to be like 0 0 1 0 1 1 or something. I think it's just going to be nonsense because we we accidentally bound it to the wrong buffer. So that's what went wrong, and that's why our triangle disappeared, because all of a sudden we're using nonsense data to be vertex positions. So let's make it not nonsense and actually bind the correct VBO to use for the a position attributes. So we'll do GL bind buffer, GL array buffer, and then we'll what did I call it? Oh, I just call it buffer. Great. That's not the best naming ever. But we know the buffer handle contains the position buffer. I should probably have renamed it actually, but whatever. So now we're binding the position buffer before we're making the attribute link. All right. So now it should be making that link between the A position and the correct position buffer. So that's what happens. There we go. Okay, we're back. Great. So now we have our positions. Let's implement the color attribute then. So I will go into test vert here. Since the vertex buffer, it's what actually getting the vertex information. We cannot get vertex information in the fragment. I think I said buffer on accident. I meant shader. We cannot get vertex information in the fragment shader just automatically that way. Vertex information is only available in the vertex shader. However, we can decide to pass information from the vertex shader to the fragment shader. All right, so I will paint this. Let's see. So, you know, we're gonna get a triangle here. And each of these vertices are gonna have a color set in the vertex shader. Oops. So this is the vertex shader. All right. So each of the vertices has the A color and also the A position, but for now we only care about the A color. And what we can do is that we can choose to pass that over to the vertex shader. No, it's not the fragment shader. Sorry, I'm a little bit loopy. And how do we do that? Well, we use the out specifier. So it's gonna look like this. In the vertex shader, I'm gonna type out vec3. I usually call it F. So F means fragments in this naming convention. So what I'm saying is, okay, I want to pass something to the fragment shader. So then I usually type them, call them F underscore. So this means, okay, I'm outputting from the vertex shader. And what that means is it gets passed to the fragment shader. All right. So I'll just do F color is equal to all right, and then we, of course, I forgot about this. We also need to declare the attribute here, so A color. So again, it's in, which means it's input to the vertex shader, and those are the attributes. It's a vec3 because remember when we bound the attribute, we said it was 3 floats. So that's why we're doing a vec3, and I'm calling it A color. So again, A for attribute and it's color. And again, the order matters. So the first attribute is by default bound to 0, and then the second one is bound to 1, and then the third one is bound to 2, and so on. It just increments, all right? So that's how I knew that the color should be attribute index 1, because I sort of had in my head which order we were going to do this in the vertex shader. Okay, so now we've gotten the attributes in. And we're gonna pass it to the fragment shader by setting this F color here. So I'm just gonna say F color is equal to A color. Okay, cool. And then in the fragment shader, so I'm gonna in the fragment shader say we are getting an input from the vertex shader. So I'm gonna type in vec3 F color. It's very important that the name is the same. All right. This is why I don't want to call it O in the vert shader, because the name has to be the same. And if the name is O color, that's going to be very confusing because we already have O color here, which is the output of the fragment shader. So that's why I usually call it F underscore. So here we're declaring an input. And again, this time it's not an attribute. Since we're in the fragment shader, this is not, in does not say it's an attribute. In means something got passed to us from the vertex shader. All right, so I'm declaring in vec3 F color, very important, the name has to be the same. So now we can reference what the attribute was in the fragment shader. So I'm just gonna set here F color. And you know, this is GLSL magic. So if I do vec4 and then give a vec3 and then 1, this will say set the first 3 components of the vec4 to the XYZ of f color. So no, XYZ will be whatever the XYZ is of f color, and then for the alpha component do 1. Right. So this is called something called swizzling. Not super important, but okay, that looks cool. That looks kind of interesting. Not exactly what I thought it would look like, but it was supposed to be like red, green, blue, white. But it's something, okay? So why is this happening? Again, want you to look at the code and make a guess why we're seeing what we're seeing here. Okay. And hopefully you've seen that it's the same issue again. We forgot which buffer is bound when we call GL vertex attribute pointer. So here we're calling bind buffer, which is the position buffer. So we're binding the position buffer, and then we're binding both attributes to the same buffer, which means that the opposite of what happened before is happening. That instead of binding a color to our nice color buffer, we are instead binding it to our position buffer, which means that, you know, it will treat the lisping, it will treat these 3 components as a color, and then the next 3 components as a color, and so on. So again, we have to be aware of which buffer is actually bound when we're calling GL vertex attribute pointer. Oh, excuse me. So we're just gonna bind our color buffer here. Oh dear Lord. There we go. Hey, there we go. So it looks very funky, and that's nice. So a feature of GLSL is that when you're outputting data from the Vertex Shader to the Fragment Shader, it's sort of not obvious what's going to happen in the in-betweeny bits, right? Because Fragment Shader runs on every single pixel here, right? While the Vertex Shader is running on just the 4 corners. All right, so the Vertex Shader is outputting data like here's red, here's green, here's blue, here's white. It's outputting that to the Fragment Shader. But the Fragment Shader runs on a hell of a lot more pixels than that, not just the corners. So the way GLSL has handled that is by in-betweeny bits blend the color. All right, so it's blending the color in between each of the vertices, and this is true for all data you pass in between the Vertex Shader and the Fragment Shader. All data will always be blended in between those 2 vertices, and this is extremely useful. You don't want just the data for the corners, you want to blend the data in between the corners. This is very important to make a lot of things work. So that's why, you know, from red to green we're blending and getting this yellow, and, you know, between green and blue we're getting this cyan, and in the middle we're getting, you know, a sort of gray magenta color. Cool. Great. So I'm gonna take a little quick break, and then we're gonna look at something called interleaved buffers. Very cool. I'm back. All right, so we did multiple buffers, and that was cool. But what if I told you we could get multiple attributes out of the same buffer? And that is called something called interleaved attributes. Hold on, let me just close this book. All right. So how would that work? Let's just draw it out, okay? So the way we would do it in that case is that we would, let's see. We would just sort of place out all of the data of one vertex one at a time, okay? one vertex at a time, I would say. So we would go, negative 0.5, negative 0.5. So that's the position, and that would go the color of that vertex. So we'd say it should be red. 0, 0. And then we'll replace, okay, what's the second vertex position? So that should be 0.5, negative 0.5, and then what's the position of that vertex, of the second vertex gonna be? So it's gonna be green. Oops. And then, so on, each of the vertices one at a time. So you define like each of the attributes for every vertex in a row, like that. So let's do that. Let's reuse our first vertex. So instead of using two different buffers, one for position and one for color, we're just gonna use one buffer for both position and color. Okay. So I'll remove that, all of the stuff we just wrote. I'll remove that as well. So we don't get a compile error. And then I'm just gonna write the data for each vertex one after each other. So on the first vertex, we're gonna have minus 0.5, minus 0.5. As a row, I'm gonna write the color of that vertex. That's gonna be red, like so. And then the same for the second vertex. So here's the position, and then I'm gonna write 0, 1, 0. So that's green. And then for this third vertex, I'm gonna do green, blue. I'm waiting for my dinner, so I'm sorry if I'm a little bit loopy. I'm quite hungry, but it's okay. And then for the top left vertex, we're gonna make that white. Okay. Cool. So now if we compile this, should compile, yeah, if we run it, it's gonna be nonsense. Yeah, okay, this looks, this is nothing. So it's, the binding as we've set it up is just like take the data in pairs of 2 for the position. So it's just gonna be like, take these 2 and then take these 2 and then these 2 and so on. And that doesn't work anymore. Like we've interleaved the data. So, it should instead, let me just remove this. Instead, we should say for the position, read 2, then pass 3. So then you just jump over 3, and then read this 2, and then pass over 3, and then read this 2, and then it will actually get the position of each vertex correct. So how do we define our attribute to, like, read 2, jump over 3, read 2, jump over 3, read 2? Well, this is something called a stride. Stride. Okay, so that's the stride of the attribute. And how do we define that? The stride is the distance from the first byte of an attribute data. Distance from the first byte of attribute data to the next first byte. Okay, that made very little sense. I'm gonna draw it. It's the distance from the first attribute to the second attribute, like this. So the distance from the not attribute, it's the distance from the first vertex to the second vertex. So there we go. In bytes. Okay, so how many bytes is it between this first vertex to this second vertex? Okay, so it's essentially defining how big is the data for one vertex in bytes, and that's called the stride. So, okay, let's just do the math like in our head first before we actually start coding anything. How big is one vertex in our VBO? So it's 5 floats. Okay, so this is like the size of one vertex. So it's 5 floats. 5 floats. And okay, so how big is one float? One float is 4 bytes. So it's 5 floats times 4 bytes per float. Per float. So that's equal to, what's 5 times 4 is 20. 20 bytes. So with the stride, we're telling OpenGL when you're rendering this, don't do them right after each other. So that's what a stride of 0 is telling OpenGL. A stride of 0 is saying the attribute or the vertices are just right after each other for each for the attributes. So it would read 2, and then it would just read the next 2, and then it just read the next 2. So it's just sort of assuming that each vertex is just this data. It's just the position in this example. There's nothing more to a vertex. That's what happens if you provide a stride of 0. So let's do this. So let's go into OpenGL here. And that's these last 2. Actually, it's just this 4th here, or 5th, I think. Here you're saying, okay, stride. So we were providing 0, which means that, it's we're saying to OpenGL there's nothing more to a vertex than just this attribute. But now there's more. So we're going to provide 4 times 5. All right. We could write 20 if we want, but we can also just write 5 times size of float. This is probably the most clear way of writing it. What we're saying is each vertex contains 5 floats. So when you start reading the attribute of the first vertex, you have to jump 20 bytes to get to the next position. And then you have to jump 20 bytes over to get the next position, and so on. Great. So let's compile and see what happens. Okay, great. All right. So this is what we expect. So now the position of each of the vertices is correct. Great, because when it's passing in the first attribute, it's then jumping 20 bytes to get the next attribute, and then jumping 20 bytes to get the next attribute. Sorry, vertex. I'm mixing up those 2 words. Hopefully that made sense. I might have to like re-record this when I'm not like super hungry or something. I can feel like my words sluttering. But yeah, now I'm already halfway in, so let's just do it. It's fine. I should stop being so self-conscious. Okay, so anyways, how about the color then? Well, if we think about the stride of the color, so let's start with that because that's what we're working on right now. If we're thinking about the stride of a color, well, the distance is the same. If we're thinking about, going from one color to the next, the distance is going to be the same. It's just going to be the size of just the size of the vertex, data-wise, that is. So the stride of both the color and the position is going to be the same. In fact, it's the same for every attribute in the vertex. If we have 5 attributes, like you have a normal and a UV and whatever, their stride is always going to be what is the size of all the data combined. So the stride is the same for color. So let's just write that. So it's going to be 5 times the size of the float. But it doesn't start at the same position, all right? It doesn't start at the beginning. It starts 2 floats in. And that's called the offset. Or in this case, the pointer, which I think is a terrible name for it. The pointer. Because if I, here's this convoid pointer. So what we're saying here is that the position had an offset of 0. It was the first byte of every vertex is always the position. So, you know, if it jumps the stride over 20 bytes, then, you know, the first byte there is also going to be the position and so on. But the color is offset 2 floats in. So by defining an offset, we're saying, okay, jump the stride, or in the beginning just the 0, go forwards 2 floats. And then there, those 3 components, those 3 floats are the color. And then it's gonna jump the stride to the next vertex, and there again, offset 2 floats, and there's the color. And then jump to the next vertex, offset 2 floats, read the color, jump to the next vertex, and so on. So that's the offset. So, and again, it's in bytes, so we have to provide the offset in bytes. So I'm just gonna do 2 times size of float. All right, so that's the offset of the color attribute. All right, because we're skipping over these 2 position floats. However, I don't understand why OpenGL chose to do this. You have to provide that as a const void pointer. I don't know why that is, why we can't just provide it as a number, but okay, let's just cast it to a void pointer then. There we go. So, I don't know, but we do it. So now we're telling OpenGL, when you're binding attribute 1, bind it to exactly the same EBO, or sorry, vertex buffer, the same VBO. So bind it to the same buffer, because again, we've bound the buffer here, but then we never bind another buffer on the array buffer slot, that is. We bind an element buffer, but that's a different slot, so we don't care about that. We never bind on the buffer, so we're binding both of these attributes to the same vertex buffer, but we're binding them with different offsets and the same stride. Okay. Let's check it out. Ah, and there we go. So now we have the same thing happening, but using only 1 buffer instead of 2. So why do this? What's the point of this? Well, first of all, you know, I don't know this for a fact, but I'm pretty sure this is faster on graphics cards to do this, because of something called cache retention. Now, I don't myself know exactly how the hardware of a graphics card is built, but I would not be surprised if there is something analogous to the CPU cache on the graphics card, which means essentially that data that is together is much faster to run than data that is spread out. But you know, even then, like, you know, the difference is gonna be nanoseconds, if even that, per vertex. So I'm not saying like if you do this you'll get you know, twice the frame rate or anything, but however, it's also a lot easier for me to now edit this data. You know, I can clearly see how the attributes are bound together. I will not accidentally make one too many positions, because I will easily see that the color has not been defined there. And you know, as we put in more and more attributes, it's gonna be nice to group them together into one, you know, one unit to see what the data actually is gonna be then in the Vertex Shader. So that's nice, but even then, you know, it's really a matter of what works best for each situation. So I'm not saying one is better than the other. They are both completely valid ways of doing attributes. It's up to you which one you think is the most appropriate for each situation. But yeah, we're gonna continue forward, at least with this example, doing interleaved attributes. So that's Vertex Attributes revisited. Hopefully that made as much of sense. You know, hit me up in at Discord, in the Discord channel, and I'll explain things further. I might make a new video, maybe going into a little bit more detail or explaining things in a different way, if this didn't make sense. You know, use me how you see that I am needed. So yeah, I'll see